Yeah.
So a quick question about the homework. If
Yeah.
I complete all 25 parts, does that mean I'm gonna get 25 points in the grade? Or is it actually based off what scores you get?
I think different questions are worth different amounts. The first homework, folks have had trouble with. I can see like as you like put in the answers, I can see what the distribution is in the class. So because I want to make sure that it reflects people's understanding and not just arbitrary numbers, including the fact that like I've seen people put in the right answer, the master just didn't accept 5 times. So I'll just grant you full credit, right? The first homework is going to be very lenient. It may even become extra credit. Subsequent homeworks, it'll be like the number of times you tried it with the wrong answer, because there'll be more. The very beginning of this class, you'll notice we haven't even talked about a planet yet. I've barely shown you like a star. Eventually, I'm going to show you a picture of a planet. I'm going to talk about why it looks that way, and you're going to have to qualitatively describe what's happening, right? So that will require more thinking, and you can select a real box as opposed to being like 10 to the 24, right? Some number that you've never used. Happy? Unhappy? Okay. Okay, so let's get started today. This is that picture that I told you about where you have big rocks and then the sun will set in between the rocks and it tells the people who designed them what time of the year. Pretty remarkable. This is just a version of a set of rocks. This is not Stonehenge. And then we're going to do 3 things today. We're going to talk about how the sky changes around us, around the Earth. We're going to see how scientists challenge the geocentric model. And hopefully we'll get to how Galileo was able to conclusively distinguish between the heliocentric and the geocentric model. But because we're going to do a lecture tutorial halfway through, we may or may not get through that entire bit. Okay? So just to recap some thinking about this, why does the sky look different from different latitudes? So if we think about the Earth as a sphere, we have to say, okay, so if I'm up here above 30 north, so I think we're located about here. This is the position north or south of the equator. Then I have access to the northern part of the sky. If I'm down here, then I have only access to the southern part of the sky. And as I move from north to south, I'm going to be able to see different stars, right? Longitude is this way, east-west. So if I fly across the country here, I'll still see the same stars. Doesn't change my night sky. What will change, inevitably, when I fly from here to here, I will wake up a lot later than everyone else. I'll be jet lagged. They're on a different time. The sun rises earlier for them than it does for us. This is where time zones come from, right? This is why when you're collaborating with people from Europe, they're up, they've done their whole day before you even had coffee. Like, how is that possible, right? And then you have your friend come to visit, and they wake up at 6 and they're done with their whole day before you're done with lunch. You're like, what the hell? Okay. Okay, so I'm going to take this. We're going to recontextualize this. Is this at the North Pole? Thumbs up or down? Go back 1 second. Let's see if we can put this together. Okay. Remember that we're trying to piece all of these things about the stars together. So here, how do I see stars at this location? They rise in the east and they set in the west. So let's imagine, for example, that that's north. Very convenient that someone labeled it. So I might see a star rise over here and go down over here. Okay, and that is because we are here. Okay. Is this picture at the North Pole, yes or no? Why are you saying no? Yeah. Oh, that's you're right.
I feel like it's not at the pole because, although I like the rotating in a way that's like not directly above, but
Right, okay, so let's go back a statement. So he said they seem to be rotating around here, but this is not directly above the picture, because I can see the horizon here. We have some things that set, they rise, and then they set, depending on which the pole this is, right? If we go back here, we see that if I were at the equator, okay, every single star that I saw would rise on the east and set in the west. But if I'm at the North Pole, they just go around the pole. And the horizon is the only thing that stops them from rising and setting. So I'm standing exactly at the North Pole. The stars just go. Right? Does that make sense? Yes, no? Interestingly enough, I mean, you can't do this from this picture, but if you wanted to know where you were in latitude, and you're an ancient person, or even just someone who doesn't have GPS, you can use a little angle maker. You can figure out the angle that the North Pole makes with the sky, and you can figure out where you are on the globe. Because if you're at the equator, this comes all the way down to the horizon. And if you're at the North Pole, it goes all the way above to the zenith, 90 degrees. Okay. Okay. Let's think about this question. How would the night sky look from the North Pole? Would A, all stars be circumpolar? B, no stars would be circumpolar, exactly the same as San Bernardino, or some circumpolar stars, some normal, but there would be different stars. This is your resume. Okay, 3, 2, 1. Okay, most people have 1. Anyone want to defend 1? What does the word circumpolar mean? Yeah.
Remain like actually like program. Like they remain perfectly above the horizon, so the horizon can't do anything like you're setting up the North Pole.
Right.
Basically,
Yeah, so another way of saying that is they never set. Right? So all the stars that we tend to see, say in the southern hemisphere, if you're looking to the south, not to the north, they all seem to set. They rise and they set. Orion's belt sets. North Pole doesn't set. Right? Just goes around in circles, just like we saw here. So these ones here are circumpolar. What about these ones? Are they circumpolar? No. And exactly like you said, if we're at the North Pole, all stars would be circumpolar. None of them would set. Okay. Yeah.
Didn't we say in the last picture that we were at the North Pole in this one?
No, we said we weren't.
Oh,
We weren't. No. I said you could find out your exact latitude by measuring the angle.
Okay.
I said if that were directly overhead, then you would be at the North Pole. Okay.
You can tell by the mountain, right?
You can also tell that. There's no mountains in the North Pole. It's all ice. And Santa's workshop. Okay. Here's a different question. What would the sky look like from the equator? All stars would be circumpolar except Polaris. No stars would be circumpolar except Polaris. Same as here. Some circumpolar, some normal, but there would be different stars. Okay, show me your fists if you're ready. Three, two, one. Okay, we got a lot of 2s now. Does anyone want to defend that? That's not 1, right? No one from the back row wants to defend 2? Yeah, you want?
all stars will rise and set.
Right. When you're at the equator, let's go back and look at this picture. When you're at the equator, your horizon allows you to see every star in the sky. So if you live here, right? Pretty awesome. You get to see all of the stars rise and set. And you would even see Sirius kind of do one of these little, or sorry, Polaris do one of these little circles around the pole. And then if you look to the south, you get to see the Southern Cross. Okay. Okay. Try to warm our brains up because I know that it's late, it's Friday. You just want to be watching the Dodger game, but you can't. Okay.
So the answer to the second one was.
Does anyone want to answer him? What was the answer to the second one? B. No stars would be circumpolar. Okay. So here's a question. Which way will the stars appear to circle the south celestial pole when we're visiting Tasmania while looking south? So we're visiting Tasmania, we're looking south. Which way do the stars appear to rotate around the pole? Is it A, clockwise, B, counterclockwise, C, depending on the season, D, there's no celestial south pole, so there'll be no circumpolar stars? You can even like use the room, think about your arms, think about how stars move. Remember, that would be north, that would be south, even though for some reason it's on that door. Okay, so show me your fist if you're ready. 3, 2, 1. Nice mix, nice mix. Okay, so turn to your neighbor, see if you can convince them of it, including you can stand up and think about which way the stars are going to go, right?
Yes.
You got a new already? You already know? You think so? Maybe try it. The stars right. You think your neighbor wants to Did they say yes? That's still. Okay, let's try. It sounds like it's quieting down a little bit. Fists up if you're ready. 3, 2, 1. Oh. Oh gosh. Uh-oh. Okay, it switched around. Does anyone want to defend their answer? Yeah.
So I said clockwise. For us, it's counterclockwise. It's stars in the east go to the west. It's the same south pole, but it's like
Right. So we said that the stars still rise in the east. They don't magically move to the west, but we're looking in the wrong direction. So typically, if we're looking at the North Pole, they're still going to start in the east and they're going to go to the west. So that would be counterclockwise. But if I look in the opposite direction, they're going to rise in the east and set in the west, and that's clockwise. Hey, everyone, yeah.
Does the location like change the outcome at all of like where you're at?
No, The location was a trick. But you can't see the south celestial pole from here. Why? Because we're on the north side, right? So the reason I put the location is because you have to be able to tell that you're in the south at all, right? So if I said you're on the equator, not as helpful, right? Because they don't actually circle the pole. You have to go south of it. North, south, I don't know, whatever. Not math. Okay. Whew. Folks, okay? Okay, so let's talk again about astronomy of the Greeks. So just to we've done the motions of the sky, we've warmed our brains up a little bit. What was this concept? Who's this guy, Ptolemy? I don't have to remember him. Just gonna see if you recall this. Was he important because he developed a model of the solar system that made sufficiently accurate predictions of planetary positions? Was it because he developed the first scientific model? Was it because he was the first to believe in an Earth-centric model? Or was he the first to create the model of the solar system that placed the sun rather than the Earth? Or was he the first to use perfect circles to represent all planetary orbits? Okay, put your fist up if you're ready. Okay, 3, 2, 1. Okay. Okay, Ptolemy was important to the history of astronomy because he was the one who said that we should put circles on circles, and therefore you could explain retrograde motion. He was not the first person to think about the world as heliocentric. He was not the first person to think about them as perfect circles, but he decided we should put more circles. More circles are better. Here's two versions. Here's the Earth-centric view with us at the center. And then there's the heliocentric version with the sun at the center. And as we saw when we talked about ancient astronomy, we actually had people from other civilizations that were very able to be to construct these models. And in fact, they could predict the positions of the planets thousands of years ago, but not to the sufficient accuracy of the naked eye astronomer. So they had models, they just weren't perfect, right? Because they used only the first version of the circle. They didn't have circles on circles. Okay. So they said that the Earth is the center of the universe. We said that the heavens should be perfect, that they should only use circles. This will become important because when you look at the moon today, you say, pretty circular, right? But you actually know what the moon's surface looks like. So it's a little bit cheating. They didn't. When they looked up at the surface of the moon, they just saw this beautiful bright sphere, and there was no topography for them, right? They didn't know that there were mountains. They didn't know that there were flat areas. So they assumed that they must be perfect spherical objects moving on those perfect spheres. Okay. And they noticed this fun stuff. I told you that if you go out and you look at, say, the sun, same time every day, right after sunrise or right after sunset, it'll make these really fun little loops. And they'll notice that the planets would move around in this way, this retrograde motion. They saw that Venus and Mercury stayed close to the sun. They saw that this could be explained by this retrograde motion of moving around by putting an epicycle. Okay. So if we think about it now, we say, well, maybe this was, maybe you were wrong about something, right? Because you had to make a modification to your model. Sometimes those modifications, yeah, okay, they right away explain the data, but sometimes they just get more and more complicated, right? So this was explaining this type of motion. Here's another version of retrograde motion. This one doesn't do the loop, just, oh yeah, time goes this way, sorry. Time goes like this, turns around, and then comes back. Okay, different type of loop, but it's still retrograde motion. Retro meaning to go backwards, grade would be motion, retrograde motion. Okay. So why did they get this so wrong? Right, this is an indication that something was wrong with their model that they had to fix. If they weren't willing to abandon the idea that, for example, we would even be moving. What the hell? What were they missing? We talked about it at the end of last class. Yeah. Parallax. What I'm doing right now, right? The students in the front are moving much more with respect to the students in the back as I move around the classroom. They looked for parallax. Okay? They did not see any. Right? So they looked for this. So high amount of detail. They did not see any stellar parallax. So they said, well, we can't be moving. So we have to accept this idea of epicycles as the reason for this little motion. You had to accept these loops. Was this following the correct scientific method? Scientific method? Got a couple no's. Any yeses? Yes? Any other yeses? Anyone want to defend their yes? Or defend their no?
I can admit it, it's a theory first, so then they have to find evidence against it.
You have to find evidence against it. So the evidence against it was this motion, this epicycle, or this retrograde motion, and they solved it with epicycles, right? Was there additional evidence that they were wrong? No, not yet.
Yeah.
Okay, so technically, he was still following the scientific method. And this is important because we have to wait until something really beautiful happens, which is the advancement of technology. Okay, so the Copernican revolution doesn't happen until medieval times, early Renaissance, because you haven't developed the technology necessary. Okay. I'm gonna skip this one because we're doing a lot of these. All right. So this is Copernicus. He proposed a heliocentric model. He still wanted circular orbits. Okay. This is early 1500s, and his model was no more accurate than Ptolemy's. In fact, it was worse. This is why we added epicycles. This is why we added these circles on circles. So he just changed the coordinates. He just said, okay, well, instead of the Earth being at the center, I'm going to make the sun at the center. Is that going to fix anything? No, it didn't fix anything. And you're like, well, then why does he get a revolution? That's not very smart. Okay. So this guy's great. This is Tycho Brahe, the late 1500s. This is the greatest naked eye astronomer of all time. So this is a device called an astrolabe. I don't really know how to use this. I assume it's really hard, but you essentially have to line up where the stars are on the sky with this giant thing. You like point it based on your horizon, and he would write down the locations of all of the stars, all of the planets, and just collect it in these huge tomes of data. Okay, these were the most accurate measurements with the naked eye that anyone had seen. And he created the Tychonic model of the solar system, that the sun orbits the Earth, but the rest of the planets orbit the sun. Because, we special, right? I don't know why. Okay, he was also, okay, we'll talk about his personal life later, but he was weird. He died because he felt that it was rude to get up from dinner and his bladder burst. He had a nose that was made of bronze, I think from a fight or like a duel. Got a sword fight. Yeah, he got his nose chopped off. That's a weirdo. He also wasn't really that nice. So this is Johannes Kepler. Johannes Kepler was a student of his, or an underling, so to speak. So Kepler tried to match Tycho's observations, and Tycho was like, I don't want you to take all of the credit of my wonderful observations. I'm going to give you the shittiest data set. So he gave him Mars, because Mars didn't fit to any of the circles well at all. In fact, it was like the one giving him the most headache. He's like, fine, you take the worst data and see if you can come up with anything. And Johannes Kepler actually had a breakthrough. He said, well, what if I don't use circles? What if I use ellipses? And it turns out this allowed him to match the data perfectly. So he just sent it on him, and the rest is history. So this piece you can read, but I think we should really describe what an ellipse is first. An ellipse is a squished circle. The way that I've had this explained to me when I was an undergrad and then later on is like, you can think of an ellipse. You hear the word ellipse, I think elephant. Like if you have a circle and then you squish it like an elephant sitting on top of the circle, the more squished it is, the more elliptical it is. Okay? So up here at the top, a perfect circle is one with eccentricity or ellipticity of 0. No elephant. You add a little bit of elephant, say 70% elephant, and then you kind of squish that circle down. And if it's very, very squished, say 0.9, right? Okay. It can go out to 1. That would be a flat line. Okay. Seems like a perfectly good explanation, right? Which one of these is Earth's orbit? They look like the same, right? Is this a trick question? No, this is actually, these are 2 separate shapes. Anyone a visual designer here who can see the difference in the eccentricities? What? The left one's bigger. The left one is a perfect circle. The right one is the Earth's orbit. Oh, yeah. Look at how small that eccentricity is. That's tiny. No wonder the circles work for so long. Okay? But Mars has a pretty sizable one. So the reason that Mars didn't work is because Mars actually does get closer to the sun and then farther, because it orbits in an ellipse that's fairly large eccentricity, very large ellipticity. So if we go back here for a second, the reason why Kepler was able to do this at all was because the squished ellipse is the one that fit the data. Okay. Okay, so we're going to take a quick break here to talk about the cause of moon phases. You'll say, well, why the hell do we have to know that? And that'll be because in order to understand the next piece of evidence against the Earth-centric model, we have to understand why the moon has phases at all. Can you take one of these per group and then pass the rest down? Can you take one of these per group of like 2 and then pass those down? Okay, so to begin to think about this, we have to talk about, say, the moon. If you've gone out, say, let's say you go out tonight and you look up at the moon at about 8 o'clock, you're going to look towards the southeast, and it's going to have something like a C shape. Anyone know what that phase is? What? It's a crescent. C for crescent. Okay. And if it were half full, what phase would that be? Half. Good. And if it were full, it would be full. And if there was no moon, it would be new. And if it was only kind of showing, like almost full, but not quite, this is the weird one. What did you say? What is it? It's where that tiny bit at the edge isn't shown. The smile is the crescent, like this, right? But when it's a small amount of unshaded on the side, that's called gibbous. Who knows why? Okay, so the reason why we get shading at all, I didn't just bring this because it's fun, is because the shadows, let's say I choose a light, let's see, does this light source work? I should have tested this beforehand, I'm sorry. I don't think this is a light, I think this is a camera. Okay. I have the technology. Okay. So let's say you have an object. In this room, it's not great because it's sort of uniformly illuminated. You can't really see shadows except for on the bottom. But if I'm the sun, and this is the object, okay? Now you see that one side of it is shaded and the other is not. And as I rotate it away from you, you will see different phases, right? I don't see different phases. I see the same phase, fully illuminated, because I am the light. But now, if this person were the sun, okay, and I moved it, no, it's probably too light on this side. Hold on. Maybe if I do it like this, you see different phases, right? Okay, so we're going to use these concepts when we try to answer this here, because this is going to answer a fundamental question about whether other objects, say Venus, Mars, do they orbit us, or do we all orbit the sun? To understand that, we have to understand phases, okay? And then in the meantime, we can find out about the moon and stuff. Okay, so let's try and get through this in like 15 minutes. Okay. Yeah. Okay. Does anyone missing one? Don't forget, please put your name and your last name. If you need the baseball, let me know. I love it. That is great. That is great. Gravity and green for your win. You're perfect.
Yeah. Yeah.
Yeah. Yeah. How much? One half. Yeah. Yeah, so now.
Yeah, yeah.
So what's happening? Look.
Would you, would you know how to play with the Japanese and they in the virtual?
Anyone else do baseball?
Here, yes. Then we can determine. Always very. Yeah.
So I'm gonna talk with the hands, so we're gonna. Hey, folks, how are we doing? Mostly good. How close are we? Done? Complete. And
Six for six, and now.
the jump off a bridge. Okay, which one was? Okay, I thought that I said. That one's tainted. And you're Rosalind. Rosalinda? How do you say that? All right. I'll never get Okay, so we're gonna pause discussions here. This should keep going. If you haven't finished, that's okay. That doesn't mean anything. We're just gonna let you carry those over into Tuesday. Okay? Okay. And if you do finish and you just haven't given it to me yet, just bring it up at the end. Okay, so let's talk about this reading question really quickly. Which of the following was not observed by Galileo? Was it A, 4 moons orbiting Jupiter? B, stellar parallax? C, mountains and valleys on the moon? And D, phases of Venus? Which was not observed by Galileo. Let me know when you're ready by putting a fist up. Okay, 3, 2, 1. Okay. Okay. Anyone want to defend their answer? You might already just know. How would you know that? I did the reading. Yeah.
Because I recently like I did the reading.
I read it. Okay, yeah. So that's why it's a good reading question. Good. Okay. Another way you could say this is, does anyone know what the 4 moons orbiting Jupiter are? They're called the Galilean satellites. So that could tip you off that maybe he did that one. And these ones here, well, we just talked about phases of Venus, or we just talked about phases of the moon. So hopefully that has something to do with what the hell we just did. So in fact, we'll talk about that. And I kind of alluded to this earlier today. So maybe if you hadn't even done the reading, you could have gotten beat. But hopefully you're all doing the reading too, right? Yes. Okay, good. All right. So here's Galileo. Cool dude. Italian. Cool. Galileo Galilei. Cool name. It's just like redundant. So he used this wonderful new technology that they were using in order to determine where the other ships are. Dutch folk were like, okay, for example, the reason that the carrot that you eat on a day-to-day basis is orange is because of the Dutch. There used to be carrots that were white, and purple, and orange. And orange was the national color of the Dutch. They created this huge trading empire, and they wanted to celebrate how great their country was. So they just dumped orange carrots all over the world. And so we all got used to orange as the traditional color for carrot. They developed a telescope so they could see other ships, so they could maintain their dominance over the oceans. And Galileo was like, well, that's cool, but like, what if you did like look it up, bro? And so he did. And he started to write about what he saw. And he would take this telescope, which was designed to look for stuff, on the edge of the horizon, ships, find out if it's a friend or foe, so you could bomb them before they could bomb you. And he decided he would start looking at the things that were in the sky at night. So these are real drawings of him, very artistic. You know what they say about scientists, great artists. And the first test that we're going to talk about is the phases or appearance of Venus, because this gives us a direct ability to determine whether Venus is orbiting us or if it's orbiting the sun. So we just talked about the moon. The moon has phases, yes or no? You can just shout this out. Yes, we all agree that the moon has phases. So what would it look like if the moon didn't go around us? And we could look at that picture in a few seconds. So here's an example. Here's the Earth. Here's the moon. The Venus and Mercury appeared to be going around us faster than the sun, right? That was that idea of apparent motion across the sky. But if I could zoom in, if I could use my telescope to see the phases, then I could tell whether it was really going around us, right? So if I see a phase of Venus, like let's say I see it at the half phase, or I see it full, then boom, we know that everything goes around us. And what did he see? Not phases, obviously. Okay, so here on the left-hand side, this is the idea of the Ptolemaic view. Okay, crescent, new crescent, and here's the Copernican view. Okay, here you have this version, new crescent, quarter, gibbous, full, as it moves. Now, can you really see this one? No, because it's behind the sun. That's not very easy to do. But you should see these ones here. Okay, this version here, these phases, should just be new crescent, new crescent, new crescent, right? And then as it moves around us, that would change. New crescent, new crescent, new crescent. Okay. So you couldn't, before the telescope, you couldn't see more than just the fact that it was bright. Venus, we say, is beautiful in the sky because it's really bright, right? And if you've ever looked for it, say in the evening when it comes out, or right before, or right after the sun sets at dusk, depending on whether it's an evening star or a morning star, star, I use in quotation marks, you can just tell that it's really bright. It doesn't seem to change brightness at all through the year. So most people took that to believe that that must be this, that there's really not that much changing of the phase, and that it orbits us. But what does it actually look like through a telescope? Well, it looks like this. Okay. So up here on the left-hand side, and I apologize for these dates, it's a European who did this. So it's the day and then the month. Unbelievable. And then the year, right? And so time is progressing from left to the right, and then left to right, and left to right. And what two things do you see here? You can just shout these ones out. Yeah.
When it's earlier, it's brighter, you can see more of it, but it's smaller. And then when it comes close to it, it's darker, but it's clearly.
Yeah. So two things are happening. One, the physical size appears like it's changing. Okay? And the amount that is shaded is also changing. So here in the top left-hand corner, we can see most of the shape, but it's very far away. So while it's reflecting all of that light towards us, a lot of reflection, the total size is small. And then when it gets close to us, we get more of it being shaded. And yet, it just so happens, this is one of the craziest coincidences in the solar system, those two numbers, they cancel each other out. They get almost the same brightness. No physical reason for this. It's not like some magic part of science. In fact, Mercury doesn't do this. Venus is the only one that does this. Mars gets brighter and then dimmer, and then brighter and then dimmer, because it doesn't do this. Okay, Venus is the only one, and it just gave people a headache for so long. Just so happens that the exact location it is, the amount of phase that we see, they happen to correlate. Okay, and so in fact, Galileo's observations of a gibbous phase of Venus proved that the Venus is orbiting the sun and not the Earth, because you could never see this phase if it was orbiting us. Okay, or sorry, that's not the right way to think about it. You could see these phases, but not exactly in this order. If that makes sense. Okay. So that was the first one. Now that we fully understand everything about phases, and there's never going to be a question about that again, we'll move on. The joke, we can come back to it, of course, at some point. But this is the other thing that he noticed. So he started to look at Jupiter. Jupiter is very bright, but if you use a telescope, in fact, you can see that there are more dots. So up here in the top right, I don't really know how to read this handwriting, but that's okay. So this object right here is Jupiter. That's the one that's a circle. And if we go to the telescopes on not this Thursday, but the next one, you should be able to see Jupiter for yourself. And he saw these two little dots. And he was like, that's funny. Never seen those stars before, but like this is a miracle new invention. So I'm gonna find really cool shit. And he saw this really cool shit, and then he saw another one. Whoa, that's super cool. And then the next, I forget if these are days or weeks or whatnot, but he keeps going through and he keeps watching them. And then sometimes he sees 4. And he keeps watching them and he realizes these stars are moving around Jupiter, back and forth and back and forth and back and forth and back and forth. And of course, they're not stars at all. They're moving. Okay? And so this showed that these moons are going around Jupiter. So now this gets away from this idea, well, okay, so if on one hand, Venus doesn't seem to orbit us, and there's these moons that are orbiting this other thing, maybe we're not quite the center. So let's think about everything else. Well, I guess circles are still really important, right? Spherically perfect object. Any evidence against that yet? These are perfect, right? Perfect circles. This was pretty much perfect, right? Beautiful, perfect circles. Any problems with that? Okay, so now what is he going to turn his telescope to? What about the moon? These are the first sketches that Galileo did, the moon, where he could see relief. What do I mean by that? I mean that we tend to think about, like, if you see, for example, a building shaded on one side, right? Then there's going to be sun on one side and shade on the other. He could see here, inside of these holes, that one side was dark and the other side was light. So he inferred that this must be a form of a mountain range going up and down. That he would see something like this and he said, well, that looks really flat, right? And he recorded it up here, sort of flat. Now, were these all perfect? No. Can we blame him? No. But these are this idea that these are craters or something of that type, and they're lit on one side and dark on the other. So he said we have to dispense with this idea of perfect objects. Okay? He saw mountains, saw valleys. He saw these like streaks and lines. I don't know if you can see it well, but you can see it really well on the slides when you actually pull them up at home. You'll see they have like streaks that move away from the center of these circles. So they weren't perfect circles at all. He also saw this thing called sunspots. You ever heard of those before? Those are really cool. This on the bottom is the sun. Do not attempt to see this with your eye. Won't go well. You could use special glasses to look at the sun, especially during a solar eclipse. Don't use your eyes. You will burn your eyes out. So what you can do here, this is a solar telescope. You point it at the sun, and then you project it onto the ground. And he did that too. Using the telescope, he took in the light from the telescope, and he projected it into a dark room, and he started sketching. And he found the sun wasn't even perfect. Okay, so like we can all have issues. Sun's got issues. So up here, he saw these dark spots. And if you look very carefully at them, they look kind of like they have like a dark central area and like some banding around the outside. Kind of look like a sunflower, maybe. Didn't know what they were, but he knew that they were wrong. And he would watch them move. So he could watch every day. He could see that they would move across the face of the sun. And he even figured out that the sun is rotating. Not something that you would initially assume. Sun's spinning. Okay. So using all of this, he basically said, listen, don't think that everything orbits us. And church didn't like that. So they told him, maybe just stay home for a while. Just like, don't. And so he did, because he was very devout, actually. So some people like to paint this idea that you can't have science and religion in the same view. And I don't think that's true, and I don't think he thought that was true. But he couldn't quite understand why everything was happening, right? Just because he observed these things didn't mean that he had an explanation for why they were. So, take some time to get used to this idea of like why things happen, and whether or not they happen by God, that's a personal opinion. And sure enough, Galileo was formally vindicated in 1992. So it just took some time, but everything's okay now. They didn't kill him. Also a common misconception. Okay. So let's just recap what we've learned. You have this geocentric model. Okay, this is the one Ptolemy's model, which uses this retrograde motion, loops on loops on loops. Okay, and it mostly explains, right, why the planets just seem to back up and go in the opposite direction. Copernicus had a heliocentric model, but it wasn't better. Why wasn't it better? Why did no one adopt this model?
Because the sun wasn't.
Say that again, sorry.
The sun wasn't.
The sun was in center, right? He didn't use these epicycles, and it wasn't better than polar, right? Okay, so what comes next? Kepler had a really good idea, and that idea was yeah, you squish the circles a little bit. They're not perfect circles. And we see this reiterate, right? We see the idea that, okay, maybe this idea of perfect circles, maybe that was foolish. Okay? We should have allowed for them to be a little more squishy. Maybe